it's recorded.
videographer?
He's going to do it, I think.
Yeah, but he's going to be doing Maxima to start
It's
with.
going now.
Okay, so let me give you a couple of candies. Okay, so take it away.
So how much do you want me to show, or what do you want me to show exactly?
Well, show them how to get, so there are various computer programs that let you do things that are hard to do with your fingers and just your mind, and Maxima is one of them, and one advantage of Maxima is that it's free. So maybe tell them something about downloading and installing, and then how to use it to do various things like, I couldn't get it to do a fairly simple integral, but maybe you can.
Okay, so yeah, Maxima is a free computer algebra program. You can find it if you just search for WX Maxima. The first link there will bring you to the website if it loads. Then you just go to download for Windows or Mac. And then 5.43 is the latest release. So you just click on that one and then download it, install it like normal. Then after you install it, I installed it here, and then you want to go to the WX Maxima folder, open it up, and then the actual program is in there. So this is what it looks like. It has a nice graphical interface. There's a bunch of built-in functions and stuff already in the tabs in the top, so you can just say click on integrate, fill in what expression you want it to do, like x squared times cosine of n times x with respect to x, say, and then just click OK, and it'll do it for you. You can do other things, like if you want to say declare n to be an integer, because...
So let me just ask a question. So
Sure.
You put in, what did you use as multiply? The star key?
Yes. Yeah, the
Okay.
asterisk is
So
multiplied.
star key, but for cosine you just wrote cosine.
Cosine, and then open and close the parenthesis, yeah. And then the second x here is the variable you're integrating with respect to.
Yeah, well that's quite, that's a non-trivial integral. So I guess I just clicked on the wrong thing when I tried to get it to integrate something simple.
Yeah, so this is a indefinite integral. It should have a constant, but it doesn't show constants, so you have to take that into account. You could add in bounds if you wanted by doing like 0 to pi or something like that, if you wanted to throw bounds in there.
And so you write % pi for pi?
Yeah, any of the constants in here you have to put a % sign in front of. So it's % pi, %I, %e if you're using an actual constant.
For infinity?
Infinity is just I and f, or minus
Or
I and f.
with a %? Or?
No, you can just type in regular I and f. Yeah, so, and then if, say, n is an integer, you can declare n to be an integer. And then if I recalculate this, it'll solve it treating n as an integer.
Now, what do you do to get it to calculate? You do shift return?
I do shift enter, yeah.
Shift enter, yeah.
Correct, yes.
And you see, normally you might think all you do is enter, but you have to do shift enter.
Yeah.
That's true of Mathematica also.
Is it?
Yeah.
Okay, and then other things, you can also differentiate by just doing DIFF, and then whatever function you want to differentiate with respect to, say, x, and it'll give you the derivative for it. If you have a function, say, x squared minus 3x plus 1 or something like that, you can have to factor it. Everybody knows a function that factors. That'd be whole suite of different simplification processes it can do. If you have something in terms of sines and cosines, you can exponentialize it, convert from sine to cosines into e's, and you can demorph it to get it back into sines and cosines if you have it in terms of exponentials. Yeah, so that's pretty much most of it. If you have a matrix you want to enter in, it's really easy. You just type in how many rows, how many columns, you can give it a name, and then it'll pop up with an actual box like this, so you can just type in the individual.
Well, that's easier than with MATLAB. With MATLAB, you have to figure out what the syntax is.
Yeah.
It's not very hard, but this is easier.
Yep. And then you can do all sorts of matrix manipulation, same as you could for any other computer algebra program. Yeah, that's pretty much the majority of what I had. Any other questions or things you want to know about it, I guess? There's a pretty extensive help guide you can pull up. It has an index, so if you wanted to look up, say, find roots, well, I guess you can't find it. Ironic. Yeah, but if you were to, say, have an expression for, we can do the real roots of, say, x squared minus 1, and then it'll solve find the roots for that. If you had a complex equation like plus 1 instead of real roots, you would change that to all roots, or all root.
So how do you get it to tell you what the roots are?
Too many in there. There you go. So it's just all roots, and then it breaks it down into plus and minus I.
Did you have to put in the semicolon?
No, it automatically puts in the semicolon at the end. That just separates between expressions if you have more than one per line. You can define variables or functions.
Oh yeah, how do you define a function?
Yeah, so first of all, to define a variable, you just type in the letter you want to use, and then a colon, and then whatever expression you want it to be, say x squared plus 1, right? And then you can see it changes this little name over here from, instead of being %output 16, it changed it to
So
f.
can you now say differentiate f?
Yeah, so now I could just do diff f with respect to x, and it'll do that for me. Yeah. If you want to actually make it a function where you can input things in, then that would be like f of the variable, right? And then you have to do colon equal sign, and then whatever function you want it to be. Right?
But now, suppose you wanted to have a function of x and y, what would you do?
So then I think you would just separate it. Like if I wanted to do x and y, I just do x, y, define it like this. And then
I see,
like,
colon equals, okay.
Yeah. And then do like x squared
Okay,
plus,
all right.
say, y. And then
So that's very simple. And so you can do diff f comma y and you get 1.
Right, yeah. Diff of f of x, y.
Oh, you have to say all that.
Yeah, you have to specify
Yeah.
the variable as a function and stuff.
Okay, is that it?
Yeah. Unless
All
you have
right,
anything
well,
else.
very nice. That was a very nice presentation. And let me just mention something that I think I mentioned in the past to you, namely that let's see, where does this thing go? Oh, it's back here. Here it is. Ah, okay. So, Here, well, I've got to at least give you some candy. So let me just mention something that one of my sons is a computer scientist, and he said that anybody who knows math in the sense of the sort of math that you get in this course, and knows Python, or perhaps equivalently knows Maxima, can get a very good job in the computer industry, the software industry. So it's a good idea to learn to use, especially one of the free softwares, Maxima or Python. And Python, in a sense, has an advantage because it's very, very broad. Python is also free, and Python has libraries to do things that are rather far removed from the sort of stuff that you do on Mathematica or MATLAB. Anyway, industry prefers people who know how to use free software and can do things can solve their problems using free software rather than requiring the company to purchase a MATLAB license. So let's see, we were talking about self-adjoint differential operators. We had just done let's see, we don't have a pointer today. I don't know why that thing is. So, an operator, a second order real differential operator of this form is said to be formally self-adjoint. And there are many nice properties of self-adjoint or formally self-adjoint differential operators. And the idea here is if you take any two functions u and b that are twice differentiable on an interval ab, and you integrate VLU dx, well, what you're doing is integrating v and then minus pu prime prime plus qu, that being LU. Now, if you integrate by parts once, you get that. You integrate by parts a second time, you get this expression here, which is L acting on V plus some boundary terms. And the boundary terms are the function P times the Wronskian evaluated at 2 points, B and A, and you take the difference of the two. That is called Green's formula, and it then says that the integral from A to B of VLU minus ULV dx is P times the Wronskian evaluated at B minus the same thing evaluated at A. Now, if you replace the letter B by X and differentiate that equation with respect to X, what you get on the left-hand side is this, and on the right-hand side you get the derivative of PW, P times the Wronskian, evaluated at X. And that's an identity called Lagrange's identity. So, suppose now that the twice differentiable functions u and v satisfy boundary conditions at a and b that make the boundary term vanish. So this term here is 0. Then what you have is that from Green's identity, you have that v comma Lu, which is the integral of v Lu dx, is the integral of ULV dx, because that's what Green's identity gives you when the boundary terms vanish. And now we can refer back to chapter 1, where we had a real linear operator A that acts in a real vector space and satisfies the analogous relation that the unit product of a vector with A times another vector is also equal to the inner product of A on G with F, or equivalently AG on F. And what we said then was that this operator was symmetric, or and self-adjoint. Whoops. Now, in quantum mechanics, we often deal with functions that are complex, and so what we need to do, we're going to keep L real, because the second order differential operators in quantum mechanics are typically real, but we're going to we're going to use complex linear combinations of u and v, keeping u and v real, so that psi equal to u1 plus iu2 and chi equal to v1 plus iv2. Then what we'll want is the ui vj's to have vanishing boundary conditions, to satisfy the boundary conditions, namely that p times the Wronskian of ui with vj vanishes when evaluated at b and then subtracting the value at a. And in that case, Green's identity gives us vjlui is lvjui for the real and imaginary parts. And that means in particular that the p times the complex Wronskian at b minus that at a vanishes, p being the key function in the definition of the differential operator, formally self-adjoint differential operator L. And then Green's identity takes the form chi L psi, which is chi star now, L psi, is equal to L chi star psi integrated dx. And so in Dirac notation, we write it that way. And the linear operator that satisfies the analogous algebraic relation, matrix relation, is said to be self-adjoint or Hermitian. And so that's why we call it the differential operator that I wrote down before, minus pu prime prime plus qu plus why we call that self-adjoint or Hermitian. And it's self-adjoint on the space of functions that satisfy the boundary conditions. And those were the boundary conditions that p times the Wronskian evaluated at b minus that at a vanishes. And So we have, we need the boundary conditions in order to have the operator actually be self-adjoint. And that leads us to define a self-adjoint differential system. And this is how the mathematicians think about it. A self-adjoint differential system is a real, formally self-adjoint differential operator, as we defined it earlier, a differential equation on an interval, boundary conditions, and a set of twice differentiable functions that obey the boundary conditions. And of course, they must be differentiable on the interval. So a second-order differential equation needs two boundary conditions to make the solution unique, and these boundary conditions are, the ones we'll look at are linear and homogeneous. You may encounter other kinds of boundary conditions in physics problems, but we're just considering ones that are linear and homogeneous. And that means that the space of twice differentiable functions U that satisfies the boundary conditions forms a vector space because the conditions are linear and homogeneous. And this is called the domain of the system. And for an interval, there are two sets of boundary conditions that we're going to consider. There's the Dirichlet boundary conditions, which is that U vanishes at both endpoints, or Neumann's, which is that the derivative of U vanishes at both endpoints. Now, sometimes we'll mix the boundary conditions, but for now, we're going to be considering functions that either are Dirichlet at both ends or are Neumann at both ends. The adjoint domain is technically defined as the set of all twice differentiable functions B that make the boundary term vanish when the functions U are in the domain. That is to say, the functions U satisfy Dirichlet or Neumann boundary conditions. And what you can see with a little bit of effort, not very much effort, is that if the functions U satisfy Dirichlet boundary conditions, and the functions B satisfy Dirichlet boundary conditions, then your system will work. That is, the adjoint domain, functions in the adjoint domain together with functions U in the domain will make the boundary conditions vanish. And so what we'll say then is that a differential system is regular and self-adjoint if the differential operator is formally self-adjoint, if the interval is finite, and if P, P prime, and Q are continuous real functions of X on the interval, if P is positive on the closed interval, including the endpoints, and if the two domains are the same, D and D star. And so typically what we'll think of is that domain D equals D star, and those are twice differentiable functions on the interval AB that satisfy Dirichlet or. So now that we've replaced the battery, or the tone has replaced the battery, we have more video. So so lambda rho U is then ULU integrated, and now if we just integrate by parts again and assume that the boundary conditions vanish, then what we get is that lambda times the integral of rho U squared is E of U. And so that's just the equation that tells us that the eigenvalue lambda is the ratio of the energy to the norm. And if the norm is unity, then lambda is just the energy. And so then one can ask various questions, and instead of actually proving them, I'll just give you the answers and we can maybe move on to something else. We can ask, is the function that minimizes the ratio an eigenvalue of the Stone-Liouville equation? The answer is yes. And is the minimum of the ratio the least eigenvalue lambda of the Stone-Liouville equation? And the answers are both yes. So I think we can basically skip that and maybe go to an example, which is the infinite square well, which you've no doubt seen in quantum mechanics. So we've got a particle of mass m trapped in an interval a to b by potential v that has the value v between a and b, but is infinite outside a and b. And so the potential in this case looks like this, and this is v, and this is a, and potential here is v. So the mean value of the Hamiltonian then is this energy functional, and p u prime squared plus q u squared. Well, that is just identifying q of x with v and p with just a constant h bar squared over 2m. So we're doing a very simple example of the Stone-Liouville problem. Namely, we're taking p and q both to be constants. We then have the energy is h bar squared over 2m u prime squared plus v u of x. And the constraint is that the integral of u squared dx is equal to unity. So we've taken the weight function equal to 1, and the eigenvalue equation is this, and we can solve this by using sine functions, and this particular sine function is such that when x is equal to a, it's the sine of 0, and that's of course 0. When x is equal to b, it's the sine of n pi, and that's also 0. So this satisfies the Dirichlet boundary conditions. And we can then compute what the lambdas are, and in fact, they're equal to the energies, and those are 1 over 2m times the second derivative here pulls out a n pi over b minus a squared and multiplies it by h bar over 2m and u a of b. So those are the energies. Another example is the harmonic oscillator example. And there, v would be x squared, but again, the function p is just a number, and the normalization is this condition. And so we have the Stone-Liouville equation is this, and or equivalently is this, and this of course is the standard harmonic oscillator equation. The easy way to solve this is to factorize it. And the way one factorizes it is you take advantage of the fact that this is something squared minus something else sort of squared, the square of the derivative. And so you write it in this way, and then, whoops, what happened here? Then the lowest eigenvalue is one such that this term annihilates u and just gives 0. So the equation is h bar omega over 2 is equal to lambda. So lambda is h bar omega over 2. That's the lowest eigenvalue, and that must satisfy, the eigenfunction must satisfy the equation that this annihilates the eigenfunction. And that's an easy equation to satisfy, namely just write it as an exponential of something, a constant times x squared, and then you solve for the right constant by differentiating. And one can then show that the higher order eigenfunctions are of this form, and if you relate x and d by dx to p and q, then you can see that this is like a creation operator. Namely, if the annihilation operator is p plus iq, then the creation operator is p minus iq, and that gives us this expression. Bessel's. Are there any questions? I've been talking a very long time without a question. Well, Bessel's energy function is of this form, where n is an integer, a non-negative integer. And if we try to minimize this over the set of twice differentiable functions on the interval 0 to 1, that are normalized functions, then what we wind up with is this equation. And changing variables, one can identify this as Bessel's equation. These are the ordinary cylindrical Bessel functions. And the cylindrical Bessel functions are rather complicated functions. What one can see is that there are an infinite number of them, and the eigenvalues lambda go to infinity. That was also true in the two previous examples, because in the case of the harmonic oscillator, the eigenvalues En is h bar omega n plus a half. This is the nth eigenvalue. As n goes to infinity, the eigenvalue goes to infinity. For the simple Hamiltonian of minus h bar squared over 2m d2 dx squared, so we're just talking about p squared, the eigenvalues are just p squared over 2m. And these are continuous eigenvalues. As p goes to infinity, the eigenvalue goes to infinity. And so in all three of these cases, as we go from the eigenfunction that minimizes the Hamiltonian, or the energy functional, we go from the one that minimizes it to successively higher eigenfunctions with higher eigenvalues. We find that eventually the eigenvalues go to infinity. Turns out that that's a very important property, because when the eigenvalues go to infinity, the eigenfunctions turn out to be complete, and then one can represent an arbitrary function of terms of these eigenfunctions. And that's really important in quantum mechanics, because the idea in quantum mechanics is that we have these wave functions, and these wave functions can represent an arbitrary state of whatever the system is that we're talking about. So let's recall now that a regular SL system is a set of regular and self-adjoint differential systems that have the same differential operator, interval, boundary conditions, domain. differential equations are of Sturm-Liouville type, each distinguished by an eigenvalue. So this is a definition of a regular SL system. Functions of P, Q, and rho are real and continuous. P and rho are positive on the interval. The wave function may vanish, but only at isolated points. And since the differential systems are self-adjoint, we get the boundary conditions to vanish, the boundary terms vanish, and so the differential operator is obeys Green's equation effectively, where it's manifestly self-adjoint, and one then has that if psi I and psi j are two eigenfunctions of the SL differential equation with different eigenvalues, then on multiplying one by the other and so forth, we get this equation here, and on the right-hand side, in other words, we multiply this by, say, psi j star and integrate. This is an integral of psi j star, psi I rho dx, and we have the difference of the eigenvalues. If we set I equal to j, then clearly this left-hand side vanishes, and so we get the equation that the ith eigenvalue has an imaginary part that vanishes at least, and it vanishes because the function psi I is normalized, so that coefficient is not 0. So then that tells us that since the imaginary part of the eigenvalue vanishes, the eigenvalues are all real. And so this is the functional form of what we had in terms of matrix algebra in chapter 1, namely that the eigenfunctions of the eigenvectors of a Hermitian operator have real eigenvalues. We saw that in chapter 1. Here, we've gone from matrix algebra, in which the vector has a finite number of components, and the Hamiltonian is just a matrix, and we say that if the Hamiltonian is, or if the operator is Hermitian, then the eigenvalues are real. Here we've gone to vectors that are infinite dimensional because whereas previously we had something like Vn, where this is V1 ... Vn. We've gone from that to Un, well, I shouldn't have used N, Ui, or since we were talking psi I of x goes from a to b, or from minus infinity to plus infinity. So this is a vector with continuously infinitely many components corresponding to every value of x. And so we have a much more general situation here, namely that the eigenvalues of an SL differential equation are real. Once we know that they're real, we can rewrite this equation. We've got 0 over there, but now psi j is real, so we just have psi I minus psi j. We get this equation. So now if the eigenvalues are different, then this term is non-zero, and we get that the eigenfunctions are orthogonal. And so we know then that if we have a regular Sturm-Liouville system, the eigenvalues are real and the eigenfunctions are orthogonal, at least when the eigenvalues are different. Okay, we're actually out of time now. Are there any questions? I don't think we had a single question except the ones that I asked the student during the Maxima description. All right.